We have this theoretical linear model, and we estimate its parameters using least squares regression. These estimates have standard errors associated with them, and if our assumptions hold, they each follow a t-distribution. We can then perform statistical inference. We can use these estimates and distributions to make statements about the parameters. When you fit a model in R, this is the summary output you get. It tells you the formula you used. It gives you the quantiles of the residuals. So this is the minimum residual. This was the median residual, etc. Then under coefficients, it gives you the estimates for the line, which was y hat equals negative 0.0127 plus 0.017964x. And then there's this other stuff about the standard error and t-statistics, residual standard error, multiple r squared, etc. It calculates a standard error for each estimate. And we don't need to get into the formula for that, but recall that a t-statistic is of the form statistic minus parameter divided by the standard error. We can use this standard error column to compute a t-statistic. The t-value column gives you the t-statistic under the null hypothesis that the parameter equals 0. So in this one, our model is this t-statistic for Beers is testing the null hypothesis that the coefficient multiplied by Beers equals 0. And it's a two-sided test. The alternative will be that beta 1 is not 0. Here's the calculation of the t-statistic for the slope. Under the null hypothesis, beta 1 equals 0. You get 0.017964 divided by 0.002402, and that is 7.479. N equals 16 in this case, and for simple linear regression, the t-statistic will have n minus 2 degrees of freedom. The p-value is twice the area ahead of 7.479 on a t-curve with 14 degrees of freedom. This is 2.97 times 10 to the negative 6, so it's very small. The 3 stars here tell you that it is significant at the 0.001 level. We reject the null hypothesis and conclude that the parameter is not 0 at this level, or even something below that. This t-test is saying that the parameter belongs in the model. The model is this. And we concluded that beta 1 does not equal 0. If we had failed to reject the null hypothesis, we would conclude that our model looks like this. And that's saying that blood alcohol level is just some constant plus some error term and isn't impacted by how many beers you drink. If you fit a simple linear regression without a slope, you just get the mean of y. The linear regression equation is always giving you the mean of y given x, but in this model, there is no x, so you get the mean of y. Notice that the p-value for the intercept is pretty high. Since there's no evidence that it's different from zero, should we drop it? No, because it's there to improve the fit of the line. I can't think of any case where you'd want to perform inference on the slope, and you would only drop it from the model if you have some good reason for doing so. We can use the standard error to create a confidence interval for a parameter. It's the estimate plus or minus the t-critical value times the standard error. In this instance, I want a 95% interval, so I'll use the 0.975 quantile from a t-distribution with 14 degrees of freedom. That's QT 0.975 14 in R. And we are 95% confident that the mean increase in BAC from drinking one beer is between 0.0128 and 0.0231. We're 95% confident that this interval contains the slope parameter. What R calls multiple R squared is what most books simply refer to as R squared. It's defined as the proportion of variation in the data that is explained by the model. When we get to multiple linear regression, I'll talk about adjusted R squared, but here we're doing simple linear regression, so we don't care about the adjusted R squared. In simple linear regression, R squared is the correlation coefficient squared. It's a way of measuring how good the fit is. Usually you want R squared to be, say, greater than about 0.49, and that would mean a correlation coefficient of something like 0.7. But you'll see them as low as 0.1 in some fields. Finally, this F statistic is for another test that's used in multiple linear regression. It's testing to see if at least one parameter other than the intercept is different from zero. In simple linear regression, we only have one parameter other than the intercept, so it's equivalent to the t-test on the slope. You can see that it's giving the same p-value, and this F statistic is the t statistic squared.